So I started the recording. So today we're going to solve some questions from the end of chapter problem from chapter 8 and chapter 9. Okay, so similar to the assignment problems. But before I do this, you know, I will just summarize some of the most important formulas that we need to remember or to know how to use if you'd like to solve any MOSFET transistor problems. Okay, so if you remember in saturation, okay, so in saturation, okay, we mentioned that, you know, the most famous formula is that ID equals half mu n C oxide, okay, and this value here we call it Kn prime, okay, times V over drive, sorry, times W over L, or yeah, the width over length, times V over drive square, okay. And if we have a, this is for NMOS, okay. If you have a PMOS, this is just gonna be Kp prime, okay. So for PMOS, so the same thing is ID equals half mu P C oxide, and we call this Kp prime, W over L, and this is V over drive square, okay. So this is for PMOS.
And V over drive is VGS minus VTM?
That's correct. So I'm going to define them here. So V over drive is VGS, okay, minus V threshold N, if this is NMOS, okay? So this is for NMOS. How about for PMOS? For PMOS, we call it V over drive magnitude, okay? This equals VSG, okay? VSG. So this is the gate to source, and this is the source to gate, okay? Minus V threshold P as a magnitude, okay? So this is for PMOS. Okay. So this is how we define V over drive, okay? Also in saturation, so this is in saturation only, okay? So this equation valid only in saturation. It's not valid in triode mode or cut-off mode, okay? Only in, also in saturation, you have to have VGS greater than V threshold N, okay? This is for NMOS, okay? And VSG should be greater than V threshold P magnitude for PMOS. You will find all these equations in the introduction file, if you go back to the introduction file that we had long time ago, okay? Also in saturation, in PMOS also, you have to have VDS should be greater than or equal to V over drive. Remember, these are the two conditions to set the transistor in saturation, to have the VGS higher than the threshold, okay, and to have VDS higher than V over drive, okay. In the case of PMOS, then VSD in this case, it's going to be SD, should be greater than or equal to V over drive as a magnitude, okay. So these are the DC equations that guarantee that the transistor, the MOSFET transistor is in saturation, whether it's PMOS or NMOS. You can put them in a table or Okay. So this is the first set of equations. Now, if we would like to find the AC parameters out of these DC parameters, look, mainly we find ID, okay, and then we move to the AC parameters, right? Can I erase this one now?
Yes, sir.
Okay. So for the AC parameters, okay, and of course the transistor has to be in saturation, because saturation is the region in which the transistor works as an amplifier, right? Similar to the bipolar junction transistor, an active region. So saturation here means active region in the bipolar junction transistor. So how to find the two parameters? The two most important parameters are GM and RO. Okay. These are the two parameters that you calculate after you finish the DC analysis to go to the AC analysis. Okay. Because we all know that the gain of most of the amplifiers is somehow multiplication between GM and RO, right? So we need to find GM and find RO to find the gain. So how much is GM? If you remember, it was T2 ID divided by V overdrive. Okay. And of course, you know ID from the previous thing, so you can also find other two ways to calculate GM. Okay. And for RO is V early. This is called the early voltage. So ID is the drain current. V overdrive is the overdrive voltage. VA is the early voltage. So VA is the early voltage. And it's a constant, okay? And early is a name of a person, right? It's not an adjective, it's a name, okay? So according to the one who discovered this voltage, we call it early voltage. So RO is VA over ID. Okay. And if you know the early voltage per micrometer, which is called VA prime, if you remember this, we have to multiply it by L to get VA. So VA is VA prime times L divided by ID. Okay. So these are the two AC parameters that you're going to use in AC analysis as a function of the DC parameters. Okay.
Real
Yes.
quick, sir, sorry to bother you.
No problem.
For the early voltage, will the VA prime, will it be given?
Yeah, either VA or VA prime. One of them will be given.
Okay.
If VA prime is given, then you have to also get L or find it somehow to multiply them, because this VA is in volt, okay, is in volts. But VA prime is in volt per
unit length.
micrometer, per unit length, okay, meter or micrometer or whatever.
Yeah, because I think the third and the fourth question on the paper that you gave us, the assignment sheet, were both questions just like finding find W and L, and both had VA prime given. So I just want to know if that's the same thing as, like, let's say on the exam, if we get the question, will we?
Yes, yeah. So either to get a VA directly, or you get VA prime and somehow you find L, you multiply them to find RO.
All right, thank you.
Okay. Now, if you'd like to find GM times RO, assume this is the gain or part of the gain, then you can find that if you multiply this by this, so this is going to be 2ID. I think one of the questions have this, V overdrive times VA over ID, right? So this is GM and this is RO, and you cancel this ID with this ID and you get 2VA over V overdrive. So this is another equation of GM times RO. Okay. So these equations, these 6, 8 equations are very important to solve as a basic, like plus, like, beside all other equations that we derived, you know, for the lectures, you know. But these are the basic equations to solve most of the questions about MOS amplifiers or MOS transistors. Okay. Any questions? Okay. Let's now start by solving question 8.6. Okay. So I'm gonna solve some adjacent problems, you know, like maybe in the assignment you have 8.5, 8.2. So I'm gonna solve now 8.6. Okay. So let's go to the textbook. Let me share the screen first. So this is question 8.6, okay? It's a design problem. When you see the D next to the problem, means that it's a design. So most likely you're gonna find W over L, W or L, you know, find R, you know, find the parameters or the components in the circuit. Okay, so you have a current steering amplifier here, or a current source. And it's fabricated in CMOS technology. When you see CMOS, means complementary metal oxide. So you have both. You have PMOS and NMOS. And if you look at the circuit here, you will find that this current mirror is a PMOS, right? How did you know that it's a PMOS? Because of the arrow is getting in. Okay, so this is PMOS, this is PMOS, this is PMOS, but these two are NMOS. Okay, so these two current mirrors are PMOS, but this one is a CMOS, an NMOS. So both of them, we call them CMOS. So if you have both PMOS and NMOS at the same time in the IC, we call this a CMOS technology. Okay, and I probably studied this in the digital logic design as well. Okay, we know that, so let me write these values here. We know that mu n C ox or Kn prime, so Kn prime is 400 micro ampere per volt, and Kp prime is 100 microamperes per volt. Okay. You have also V threshold N as 0.5 volt. You have V threshold P as negative. This has to be negative. Okay. And you have VA early, so V early prime N. So this is the V early per unit length as 5 volt per micrometer. And V, of course, this is for NMOS, and for PMOS, you have V early P prime as also 5 volt. So this is the same as this one. Okay, so this is the same as this one. Okay, if all devices have L is 0.5, so this now L is given, see? So L is given now, so you can multiply this by this to get V early, right? So this is 0.5 micrometers. And the question is to design the circuit so that you have I reference, so I ref is 20 microampere. So this is my reference current. I would like to replicate this current. So as you can see here, we need, this is IREF here in Q1, passing through Q1. I need to replicate this IREF at Q2, at Q3, and then at Q5, okay? Maybe I'm not gonna replicate it exactly the same, but at least with the ratio of the geometric ratios of these transistors. So let's see. So we need to have IREF as 20 microampere. This is the perfect current that I designed, and I need to replicate it at I2, but I2 now is not IREF. It's how much? It's 100 microampere. So what does this mean? It means that I2 is 5 times this one, right? So this is 5 times IRF. Okay. Now,
Could you please say that again?
Okay, let's go back to the circuit. We know that this is a current mirror, right?
Yes.
Remember how much was the current here with respect to the current here?
Shouldn't it be same?
No, it's same if you have the same ratio, W over L ratio. But remember that we have I, let's say I2 over IRF
is equal to W over L ratios of both of them.
Exactly. So if the W over L ratios are the same, then these are the same. But now I would like to have I2 is 5 times IRF. Right?
Oh, okay. Okay, nothing. Thank you.
You get it? So I have to have the W over L ratios 5 times to get this sign. So because you'd like to replicate the current in another place, not exactly the same. Maybe the other place needs more current. And you already designed a perfect current source here, and you'd like to have I2 as good as this one, but as high as 5 times as, okay? So this is why you use the different ratios, right? Okay, so we need to have I2 as this, I3 equals I4 equals 40 microamperes. What does this mean? These are 2 times IRF. Okay. I5 is 80 microamperes, which is 4 times IRF. So I need to replicate this IRF in 3 places. In one place, I need to replicate it 5 times. In one place, I need to replicate it twice. And in the third place, I need to replicate it as 4 times. Okay, these 3 places are here. So this is 1 here, Q2, 2 at Q3, Q4, because they carry the same current, and the third one is at Q5. So this is why we call this current steering, okay, circuit.
Please, can you repeat that from I3?
Okay, I1 is the same, is replicated at IQ, okay, at I2, okay, IREF here, which is IQ1, is replicated here because this configuration, when you connect one transistor as a diode connection and you connect the gates together, this makes the current here, I'm not saying the same, but replicated a multiple of IREF. And this multiple factor is 5, right? 5 times. Now the same thing, if you see this one is parallel to this one, right? So you need to replicate this here, okay? This is the same thing, you know. Now the gate of Q1 is connected to the gate of Q3, similar to the gate of Q2. So Q3 will carry a current that's a replica of our IRF, but multiplied by a factor, you know, like it's the same current, but this case is gonna be 2 times. So we have to design W over L of Q3 to be 2 times higher than Q1, and Q2 to be 5 times than Q1, and so on. So Q3 is a copy of IRF, but multiplied by 2. And since Q3 and Q4 are in the same, sharing the same current, because any current will be here, will be the same as this current, will be the same as this current. Why? Because the gates carry no current, right? The gate here doesn't have any current, the gate here doesn't have any current. So you assume that any current is in Q3 will be the same as Q4. So Q3 and Q4 will have the same current. So now you replicated Q3 and Q4, you replicated the same current, I3 and I4 will be the same. You cannot make a ratio here, okay? Now, this Q4 and Q5, these 2 transistors are connected in a current mirror fashion, right? One of them is connected as a diode and the gates are connected. So that means this is a current mirror. So I5 will be a replica of I4 according to the ratios of W over L. If they are the same, then they will be exact replica. If the ratio is different, then they will be different. Now we need I5 to be 80 microamperes. So that means 4 times, actually 2 times, not 4 times. Sorry, 2 times. Oh no, so this is 20. Okay, so it's 4 times. That's correct. So 4 times IREF, right? Did that answer your question?
I have a question.
Sure.
So for I5,
Yes.
it should also be equal to 2 times I4, right? Since it's in a current mirror with Q4?
That's correct. That's correct. That's correct. That's definitely correct. So this is 2 times I4. Yes. And this is what we're gonna use, okay? Because I5 is not directly connected to IREF. It's connected to IREF through I4, okay? You're right. So we're gonna use this, not this one.
So are you going to just find the ratio between the currents and the reference current, and then use like W, like the?
Yes. Yeah. Basically, this is a repetition of W over L ratios. We're gonna repeat, but we need to know because actually we don't have W's here, right?
Yes.
We have L, and I think L is the same for all transistors, right? Is it right? So if all devices have L, so this is common L for all devices. Okay, so I think the question now is how to find W for each device, right? Using these ratios, right? Okay, so let's think about it, how to find this one, okay? So let's continue. Maybe we have something here before we start. So yeah, use the minimum possible device width. So we need to find the minimum width. So we're not gonna design for a large width, just the minimum one, okay? Because we need to fabricate this IC as small as possible, as much, you know. And needed to achieve proper operation of the current source Q2. Yeah, for the Q2, for voltage and at its drain as high as 0.8 volt. Okay, so let's go to Q2. Where is Q2? Q2 is here, right? We need to have, you know, the design says to you that the maximum V drain for Q2 is 0.8. So I'm assuring you that Q2, this drain voltage here, can you see the cursor? The drain of Q2 is not gonna go above 0.8. Okay, so let's think, what does this mean? Okay, so if you guarantee that VD2 is maximum value, its maximum value is 0.8, so what does this mean? Okay, and proper operation of the current sink Q5 with the voltage at its, yeah, so Q2, the proper operation says the VD maximum is 0.8. For Q5, the VD minimum is minus 0.8. Okay, so for this transistor, VD minimum is minus 0.8. For this transistor, VD max is 0.8. Okay, and the question is to find the width, you know, that like W1, W2, W3, and so on, of all devices, and how much is the value of R, and also find the output resistance of the current source Q2. We need to find the output resistance of Q2. What's the output resistance of Q2? So first of all, we need to find W1, W2, and so on up to W5. Okay, so this is the first question. The second one is to find R, the second requirement. The third requirement is to find the output resistance of Q2 and Q5. What does this mean?
So like RO?
That's correct, RO2 and RO5. That's
okay.
it. So these are the 5 requirements: to find all the widths, to find R, to find RO2 and RO5. Okay? Let's start. I'm gonna erase this because I don't have space to, so I will erase this. Okay. So let's think first, what do we mean by the 0.8 is the maximum? Okay, so VD maximum, VD1, huh? This is VD1, max is 0.8. Okay, can you see the board like this, or?
Yes, sir.
Because I don't want to switch between the two, okay?
Perfectly fine.
Oops. I don't know how to amplify this. Okay, so the voltage here is the maximum voltage of VD2, VD2 is 0.8. What does this mean? If VD2 max is 0.8, what does this mean?
Does that mean that VD1 would also be 0.8?
Yes, but let's focus on VD2 now. Doesn't this mean that VDS, okay, or let's say in this case, because this is a PMOS, VSD2 minimum. How much is VDS2 minimum?
Like 0.2.
That's correct. Why? Because VDS minimum is VD minus VS, VS minus VD. And we know that VS is 1 volt, and VD will go maximum to 0.8. So the difference is minimum 0.2, right? Like VS could be 0.8, could be 0.7, could be 0.6. Okay, so the minimum VDS is, or VSD in this case, VSD is 0.2, which is 1 volt minus 0.8, which is 0.2 volts, right? Why do we need VSD? Okay, why do we need this? Okay, let me tell you, why I'm thinking this way, okay? Now we need to find W1 and W2 and these things, okay? And we said, if we find, like the equation, remember the equation ID equals half Kn prime or Kp prime, let's call it K prime, for P or N, times W over L times V over drive square, right? So I need to find, in this equation, I need to find what's the unknown variable here. Do we know the current ID?
No, we need VGS.
No, what's the unknown here in this equation?
V
What we are looking for? We are looking for W, right? Which is here. This K prime is known, right? And this half is a constant. Currents, all currents are known, right? Because you know IRF, so you know all the currents, right? So, and L is known, right? So all what you need to find is this guy here, right? To find W.
But that's what I'm saying. We don't have VGS for that.
Yes, but we're not gonna find VGS. We're gonna find V over drive from the other condition. Remember the two conditions? We said that V over drive equals VGS minus V threshold. But the other one, we have VDS is greater than V over drive, or equal to. These are the two conditions. I wrote these two equations before, okay? And this is for NMOS, okay? How about for PMOS? For PMOS, this is gonna be absolute value, and this is gonna be absolute value. Okay, and this is gonna be, instead of DS, is gonna be SD. Okay, and it's greater than V over drive absolute value. Right? So we know that the minimum or the maximum value of V over drive is the minimum value of VSD. because VSD has to be greater than or equal to V over drive. And we said the minimum value of VSD, which is the lower part of this inequality, is 0.2. So this equals V over drive. Right? Because we said always VSD has to be greater than V over drive, right? For this transistor Q2 and Q1 and all of them, you have to have the ST voltage greater than the V over drive. And I'm telling you that the minimum value of VSD is 0.2 volt. So V over drive takes this minimum value. Okay. So we know now that V over drive is 0.2. Okay. So we can substitute this value here. Okay. And we solve this equation for transistor Q1. Okay. So for Q1, we have I1. I1, by the way, is the same as Iref, right? If you look at the question, Iref is I1, which is half. And this K now, is this a PMOS or NMOS? This is a PMOS, so this is going to be KP prime times W1 over L times 0.2 squared. Okay, and this Iref is how much? Iref was 20 microampere. Okay, and if you solve this equation, everything is known. KB prime is known, L is known, 0.2 we substituted. Then you find W1 will be how much? Will be 5 microamperes. Done. So this is the first. So the problem with the first requirement is that we don't know V over drive. And how to find V over drive? You find it from this condition here, that the drain voltage, the maximum drain voltage is 0.8. So that means the maximum the minimum VSD is 0.2, which means that V over drive is 0.2. So you substitute V over drive here. Okay. So now we found W1. How to find W2, W3, W4, and so on.
Q2 has the same, like, what do you call it, same parameters as Q1, so we can find using like everything same for that too, right?
Yeah, but the current is?
The current is 5 times.
5 times. Okay, don't forget this. So we know that I2, okay, equals 5 times I1, right? And we know that I2 over I1 is W over L2 over W over L1. Right? So this equals how much? Equals 5. Because I2 is 5 times I1. We know W1 and L1. We know L, so we only need to find W2. You got it? So that means, this is W2 over L over W1 over L, because we already, L is the same, and W1 we already calculate this. This is how much? This was 5 micrometers. Okay, and how much is L? L is 0.5.
L out, right?
Sorry?
Cancel the L out. Can we?
Yeah, you can cancel them. That's correct. You can cancel these L's out. So that means W2 is going to be, if you substitute here, is going to be 25 micrometer, which is logic, right? This one is 5 micrometer. To make current 2 5 times current 1, W2 has to be 5 times W1. So you make the second transistor 5 times larger than the first transistor to have its current 5 times larger. So we are not exactly replicating the current without any factor of amplification. No. Sometimes we increase the factor, or like increase the current or reduce the current. Okay, with a factor. Here the factor is 5. Okay. Now we can do the same thing.
I have a little question.
Sure.
So can we use 2I REF equals to 1 over 2 Kp W over L multiplied by 0.2?
Yeah, yes, you can use this as well. Yes. Definitely you can use this equation, yes.
Okay.
But instead of substituting in all these parameters, this is much easier, right? And this comes from that one, because actually this ratio came from that, You have I2 over I1, right? Equals what? I2 equals what? Half Kp prime W over L2 V over drive squared. And this one equals what? Equals half Kp prime W over L1 to V over drive square, right? All these are the same. Cancel this, cancel this, cancel this, cancel this, you get this. Well, this equation actually comes from this one. So instead of substituting in the large one, you just substitute here, right? Okay, now we can do the same thing for the other ones, right? So similarly, you will find W3 equals how much? Can you tell me quickly? 3 and 4 are 4 times IREF, right? Or 2 times.
So in that case, would it just be 2 times the 5 micrometers?
Yes. So this is 10 micrometers. Because you need to make a current source that's twice as large as the reference one. So you have to make the width, and assuming the length is the same, the lengths are the same for all transistors, then the width has to be twice to generate a twice as much as the current. Okay. Now, this is this is here for Q1, Q2, Q3, right? They are the same. Why? Because they are the same type of transistors. This is PMOS, PMOS, PMOS. So we have to use V over drive using this condition of the 0.8, the positive point. But for Q4 and Q3, the situation is different. These are not PMOS transistors. These are NMOS transistors. So we cannot use the V over drive of these ones, okay? Because they work in the opposite way, okay? So how to find V over drive using the second condition that says VD 5 minimum is minus 0.8. So VD here, this drive voltage, this drain voltage of Q5 minimum is minus 0.8. So how can we find V over drive in this case? So VD, okay, 5 minimum is 0.5. Is negative, negative 0.8. we know that VDS has to be greater than or equal to V over drive, right? And VDS minimum is minus 0.8. So how much is VDS? Will be. So VD5 is minus 0.8. So this is the minimum value of VD5 is minus 0.8. So it could be minus 0.7, minus point, and so minus 0.6, and so on. So VDS is also has to be at minimum as 0.2, right? So that means V over drive here in the same thing is 0.2. Okay, but this comes from this one here, right? So V over drive in this case is going to be 0.2. And we can do the same thing to find W4 and then W5. Okay, so how to find W4? We go to the equation I4 equals half Kn in this case, Kn prime, because this is an NMOS, W over L, okay, W4 over L, because this is I4, times V over drive square. We know that V over drive is 0.2. How much is I4? I4 is 40 microamperes. So 40 microamperes equals half, and Kn prime is 400 times W4 divided by 0.5 times 0.2 square. So if you solve this for W4, you get W4 as 2.5 micrometers. Okay. So this is how to find W4. Now, how to find W5? We know that W5, we know that Q5 generates a current I5 that's a replica of I4, but with the ratio, right? So what's the ratio between I4 and I5? It's twice, right? So I5 is twice as, so I5 equals 2I4, right? So from this, we can understand this, that W5 should be twice as W4, should be 5 micrometers. Okay. So now we found all the W's of all transistors. Any question? Okay, so now let's move on to the next requirement, which is to find R. How to find R? We need to find the value of R here. How to find R? Can you give me an equation to find R?
Can we use VD, ID equals to VDD minus VDS over R and solve for R?
Yes, that's correct. But do we know VDS?
Yes, VDS is 1. VDS is 0.2.
This is the minimum. You know, this is the minimum value of VDS.
VG over I reference. The gate voltage Hello, can you hear me?
Yeah. So yeah.
Override of friends.
Yeah. So if we know VD, okay. If we know VD, okay, R equals VD over IRIF. You agree?
And VG and VD are same.
And VD is VDD. How to know VDD? How to know VD? VD is, by the way, is VG, right? Is the same as VG.
Yeah.
Right? How much is VG? Is VDD minus VSG, right? So this voltage here in the middle equals this voltage minus VSG. So we need to find VSG. Well, if you remember from the equations that I wrote in the beginning, VSG, okay, as a magnitude equals V over drive as a magnitude plus V threshold P as a magnitude. Okay. So we know that V over drive is 0.2 and V threshold P from the equation, from the question, is 0.5. So this is going to be 0.7. So now R is VG, which is VDD minus VSG. It's 1 minus 0.7 divided by IRIF, which is how much IRIF? IRIF is 220 microampere. Okay, and this gives you, if you substitute, this gives you 15 kilo ohms. Okay, so now we found the resistance R. Now, can we find the last part, which is RO2 and RO5?
RO2 is VA prime for N for P.
Yeah, RO2 is for the P. Yeah, so we need to multiply
VA prime P.
VAP prime times L, which is the same, divided by
I reference.
ID. How much is ID in R2 and Q2? What's called? The drain current in Q2.
Two I.
No, I2.
Yeah, but it's 2 times ID.
No, we know I2, we know it.
Yeah.
For R2, RO2, you need to use ID2. ID2 is called I2. Okay, so we know this, we know this, and we substitute, and this will give us 25 kilo ohm. Same thing for RO5. It's VAP times L over I5. Sorry, in this case it's VAN, right? Because Q5 is an NMOS. So this is N prime times L over I5, and this is going to give you 31.25 kilo ohm. That's it. Okay. So as you can see here, we did the DC analysis first. DC analysis means to find all the currents, find R, you know, the resistor R using DC analysis. These two steps are AC analysis, or the link between the DC component and the AC parameter. So we can use these ones to find, you know, to go ahead and do the AC analysis if we want. Okay. Any questions? Okay, let's go ahead and solve question 829. This part of the bipolar junction transistor, we are not going to cover it, you know, like just it's the same way of the MOSFET, but we already covered the MOSFET. So this is 8.9. It's a design also, and you need to consider an NMOS. So we have an NMOS transistor fabricated in, let me just move this a little bit, fabricated in a 0.18 micrometer technology. What does this mean? What's 0.18 micrometer technology?
The length, the W over L.
Not necessarily the L here, because the L, you need to find L, right? One of the questions here, find the required L, W over L, and so on. So I think this is the minimum. You know, you cannot get below this one. Okay, so let's continue and see, because this is not a number given, you know, for any of the parameters. This is you have to make sure that everything works in this within this minimum. Okay. Okay, so Kn prime. So Kn prime is 400. And this is a common value most of the time, microampere per volt squared. This is for 400 or 500 is common. And VA prime, of course, this is N, VAN, right? Because this is an NMOS, is 5 volt per micrometer. And it's required to obtain an intrinsic gain. So A node, you remember the intrinsic gain? How much was the intrinsic gain? Do you remember? Was GMRO.
GMRO.
That's correct. GMRO.
What about the negative sign?
You can have it, but you know it doesn't make any difference. We need just to find the values. Okay. Yes, you can say it's minus, but let's assume it is amplitude, absolute value. Okay. But in reality, yes, there is a negative sign. Okay. We need to have the intrinsic gain as 20, because he gives you the gain as positive. Okay, so just as absolute value, and need to have GM equals 2 milliamperes per volt. V over drive is 0.2 volt. We need to find L, W over L, and I. How? How can we work this? So we have all these inputs, and we need to find these three values.
So we solve for I to get a value.
Do we know I? I is required. We don't have I. Or you mean to find I first?
I guess.
Okay. How to find I first?
GM is equals to 2ID over.
Okay, so let me delete this. It's a GM equals 2ID over
V over drive.
V over drive. And how much is ID? Is it the same as I?
Yes, what we're looking.
Yes, so this is 2I over V over drive. We know this, we know this, so then we can find I, right? So if you substitute here, you will find I equals GM V over drive over 2, right? So if you do this, you're gonna get this is 0.2 milliamps. That's correct? So this is 2. Yeah, it's the same as V over drive because this is 2, cancel the 2, you're gonna get 0.2 milliamp. Okay, so this is I, that's correct. How can we find L and W over L?
I think we find W over L first by using ID equals to 1 over 2 Kn prime multiplied by W over L multiplied by V over drive square, and we solve for W over L.
That's correct. That's correct, yes. So let's go here, just I'll delete this. So we have I equals half Kn prime W over L, okay, times V over drive square, right? We know I now, right? We know Kn prime, we know V over drive, so we can find W over L, right? V over drive is 0.2, Kn prime is 400, I is 0.2, so we can find W over L. If you do this, you will find W over L equals 25. Okay, now we need to find L.
L will be W over 25.
But we don't know W.
Well, you could make it as a placeholder, couldn't you? And be 25L equals W. I mean 20. Oh wait, never mind.
No, we can go back to the, we didn't, what parameter we didn't utilize so far? A node. Remember that A node we didn't use so far. We used GM, we used I, we used W, you know, we used overdrive, we used KN, but we didn't use this guy. Okay, so let's do it. Let's use this guy. So A node is GMRO. We know this, right? Then we can find RO. So it's A node over GM. A node is how much? 20. And GM is 0.2 milliampere. So this is how much now? This is 200 kilo ohms, right? And we know that how much is RO?
200 kilo ohms.
No, I mean, what's the equation that you find RO? Another equation.
That's VA prime.
VA prime L over I. We know this, we know this, we know this. Sorry, we know the VA prime, so we can find it. Right? So if you do this, you'll find L equals 0.4 micrometer.
Yeah, and then from there we can solve for the width because we have the parameter. The
yes,
minimum parameter. That's
correct. If you'd like to find the width, you find it this way. But you know, here comes the technology of 0.18 micrometer. Why he mentioned this? To make sure that L and W as well, okay? How much is W? L times 25, right?
Yeah.
So if you multiply this by 25, this is going to be 10, right? So all this is greater than the 0.18 micrometer. So he mentioned this just to show you that this is, you know, the factory that fabricates these transistors cannot make anything below 0.18 micrometer. This is the minimum size that this factory can generate. So since your L is 0.4, your W is 10, then you are safe. So this 0.18 micrometer has nothing to do with the solution. It's just to show you that you are in the safe side if you calculate L and W. But if L was less than 0.18 or W was less than 0.18, then you have to find another way in your design. Okay.
RO is actually 100 kilo ohms.
Oh, sorry, 100. Okay. Yeah, you're right. But the L is correct, right?
Yes.
So you multiply I by this and you divide, you'll find this one. Okay, if you have any problem with the number, just let me know, but this is what I have. Okay, so let's move on. I know the time's flying. So let's move on and solve 841. Okay, so 841. Here's 841. He says in the circuit of figure 815. So let's go here and find 815. This is 815 here. Okay, so let me find that. So this is the circuit in figure 815. This is the original circuit. This when we replace the current source here. It's a transistor amplifier here, which is Q1, and it's loaded by a transistor, an active current source, a simple transistor, another transistor to make the current the bias. Okay. So in this circuit, also we are using the 0.18 micrometer CMOS technology. Why CMOS? Because we have PMOS, and this is PMOS, and this is NMOS. Okay, so both together, they are called CMOS technology. Okay, complementary metal oxide. Complementary means you have the N and P at the same time. Okay, for which mu N Cox, and we call this Kn prime, is 400, the same number, micro ampere per volt square, and Kp prime, this is usually smaller, 100 microampere per volt square. Okay, and threshold, we have V threshold N is the same as V threshold P magnitude, the same as 0.5, but this one should be negative, this one should be positive. And V early N prime is the same as V early P prime, as the same as 5 volt per micrometer. Okay. And you have VDD is 1.8 volt. It's required to design the circuit to obtain a voltage gain of negative 40 volt. So A, V is negative 40. Here is the negative sign here, okay? V volts per volt per volt. Use devices of equal length L. So L is the same, L1 equals L2. Operating at I equals this, so I equals 100 microampere, and V overdrive for both, okay, so it's gonna be 0.25 volt, okay, and determine the required values of VG, L, W over L, and 1 and 2. So we need to find VG, okay? We need to find L, we need to find W over L, 1, and W over L, 2. So this is a design question, okay? We need to design this circuit so that we will have this gain, provided these are the technology used, and this is the current, the bias current we need. We need to find the bias voltage at the gate for the second transistor, how much, for the current transistor, the current source transistor. How much are the L's for L1 and L2? How much is the geometric ratio W over L1 and W over L2? Okay? So how can we proceed? If you can go open the slides and see the equations for this type of bias transistor.
So, oh, okay. I thought it meant when it was saying the L1 equals L2, I thought it was saying that for some reason I thought it was talking about length of like they were going to be squares for some reason.
What do you mean by squares? The length of the first transistor is the same as the length of the second, the channel length, I mean.
Yeah, yeah. I don't know why, but I thought it was going to be a square because it was just L1, L2. Like,
oh, no. L is not the W. W is something else.
Yeah.
So the channel has an L, okay, like this, and a width like this.
Mm-hmm.
Again, the width could be greater, like not necessary to be this, like this shape here, most likely is going to be like this, this is W, okay? So W is the width, L is the length. So it's not a square, it depends on this ratio. But the L is the same for both transistors. One of them might be up to here, W is smaller, and the other one, W is bigger. But the L, the length is the same. Okay. So can we start with this gain? How much is the gain? If you go back to the circuit, how much is the gain of this circuit?
Wonder what slides would it be?
The building blocks, the first part.
Oh, okay. Yeah.
If you go back here, this one here, if you go to the small signal analysis of this guy here, this one here, slide number 6.
Okay.
Right? So how much is the gain?
Let me see. AV is negative 0.5.
Negative GM RO1 parallel to RO2. And which is correct, right? Because you have this second transistor is going to be parallel to the first one. RO of the Q2 will be parallel to RO1, right? In the AC analysis. Because this second transistor will be replaced with its RO, if you see the equivalent circuit, right? If you go back to the textbook here to make sure to see it in a bigger picture. So RO2 is parallel to the output, which is RO1, right? So RO1 parallel to RO2, as you can see here, right? Okay, now, do you think RO1 and RO2 are different or the same?
They are the same.
They are the same. Why? Because early voltage is the same and the current is the same, right? You know that RO1 equals RO2 equals V early, which is the same, divided by I, which is the same. So we will call them RO.
So it'd be the other equation where it's RO squared.
This equation will not be RO squared. It's not multiplication. This is parallel.
Oh, okay.
Can you go back to the slide?
Sure. Oops, not this one, sorry.
Yeah, can it be the one with -1/2 GM RO?
This one here.
Yeah.
This is it, right? When RO1 is the same as RO2, this is gonna be half, because RO1 parallel to RO1 means RO parallel to RO. If you have a parallel, two parallel exact identical resistors, what's the result? So AV now is GM minus GM, RO parallel to RO. If you have two identical resistors parallel to each other, the resultant is half. Here, minus GM. What's the parallel combination? It's RO divided by RO plus RO, right? Multiplication over the addition. So this is RO squared over 2RO, right? So this is half RO. So this is RO, sorry. This is negative GM RO over 2, right? So the gain is minus GM times RO over 2. We know the GM, we know the gain, we can now find RO for each transistor, right? So the idea is that you have some equations, you have to understand them first, and then know how to use them to find the unknown parameters in the question, right? So from this, we know that the two resistors are the same, the two output resistance are the same. So AV is this one. So how to find RO in this case? So we say that AV is minus GM RO over 2. And we know this, So RO in this case is going to be
That's 2AV over GM.
is GM known or not?
No, but we can find it with what is it, the V?
Oh yeah, it's not known. But we can find it, that's correct. Okay, how to find GM?
So we don't know AV. That's what you're saying?
No, we know AV, right? AV is given.
GM would just
GM is 2ID over VOV.
2ID over VOV, right? That's correct. And ID is no, right? And V over drive is known. So we have ID is the same as I, which is 100 microamperes, right? And we have V over drive is 0.25 volts. So we can find GM. Can someone calculate GM here? Because I don't have it here.
um 80 8 times 10 to the minus 4 is what I got.
8 times 10 to the minus 4 ampere per volt, right? Or mole, or 1 over ohm. Okay, now can we find L now?
Is there a formula for it?
First of all, we find RO, right? So RO, according to this, is AV as a magnitude over GM, right? So RO is AV over GM. How much is AV?
We just found that, didn't we? No. Wait.
40.
Negative 40.
Yeah, so magnitude is 40. Divided by 8 times 10 to the minus 4. Can you calculate this one?
It's like
It's 550K, right? Okay, now we know that RO is how to find L from RO, or what's the link between RO and L? V early prime times L over I. Okay, we know the V early prime, we know RO, we know I, so from this we can find L.
I have a question about RO. So shouldn't it be 2AV over GM since we multiply?
Oh yeah. I forgot this too. Yeah, sorry.
Yeah.
That's correct. That's correct. Good. So this is gonna be 100.
Yes.
So this is 2. Yeah, you're right. Okay. Yeah, I was just using the GMRO thing, you know, but in this case it's half. The gain is not GMRO, it's half GMRO. Why? Because we are putting a second transistor as a load. So that makes RO, and RO parallel to RO makes half of this. Okay, now if you substitute these values here, you should get L as 2 micrometers. Again, this is within the technology or not? The technology is 0.18, right?
So it's not.
No, it's bigger. You know, this is the minimum length or size that this factory can generate.
Oh, okay.
0.18. So if you ask this factory to generate something 2 micro, it will say that's easy. We can do this. But don't ask us to do anything below 0.18.
Oh, so what do we do if it is below?
Now, if it's below, you have to either to modify the design or to find another technology, you know, another factory, another place. Okay, but anyway, you know, everything will be within, you know, this thing. Okay, now we found L. How to find W over L? What were the requirements? W over L. Oh, we need to find VG. How to find VG? So let's go back to the circuit. We need to find this VG here. VG is the bias for the current source transistor. I know the time is flying, so I will write it down. So, okay. We know that this is a PMOS transistor, right? We know that VSG as a magnitude, okay, of the second transistor is V threshold P plus V overdrive of the second transistor, right? Okay, so we know that we know V threshold and we know this one. If you add them up, this is going to give you 0.75 because this is 0.5 and this is 0.25 volts. Okay, now can we find VG now? VG is this voltage here.
Yeah.
And we know that VSG is 0.75. Can we find this one?
Can you just subtract VDD?
That's correct, yeah. It's VDD and subtract VSG, right? Because VDD is connected to VS, right?
Yeah.
VDD is the same as VS. So if you subtract from VSG, you will be at G, right?
And because it doesn't have a resistor there to do
you don't have any resistor, so there's no drop on the resistor. Just from VDD to VG, you just subtract VSG, okay? So VDD is how much? Was 1 volt, I believe? 1.8, so this is 1.8, and this is 0.75. So this is gonna give you VG as 1.05 volt. Okay? Now, what was the second, or the next question? We need to find W over L. What's the equation to use to find W over L?
Oh, we had it earlier. I forgot.
Yeah, the big equation. ID equals half Kn prime W over L V over drive, right? Square. We know this, we know this, we know this. Now we find W over L. So if you substitute here, you get W over L. And of course, this is W over L1, right?
Yeah.
Okay, of the first transistor. And you can use it for the second transistor as well, right?
You just try to find W because the L's are the same.
Yes, okay. Yeah, no, what changes from the first to the second transistor?
The width.
No.
No.
Yeah, everything, but in this equation, other than W over L, is V over drive the same?
Yes.
Current the same? This is 1. Yes, because any current will go through 1, will go through 2, right? Any current will go here will be the same because you don't have any current here, any current here, any current here. So any current going this way will be the same. So I1 is the same as I2. So what's the only difference?
The K values.
The K, right? The K and W over L. K in the first transistor is Kn, but in the second transistor is Kp. Right? So this case, in this case, you substitute for I1, you substitute Kn and W over L1. For I2, which is the same as I1, you substitute Kp and W over L2.
So the N and the P are just like the biases, like they're positive.
No, N and P stands for NMOS or PMOS.
Yeah, okay.
This is a PMOS and this is an NMOS. So don't use Kn here. You have to use Kp. And for Q1, you have to use Kn. Okay? But the current is the same. You know, the current goes this way from VDD, go inside this transistor and then comes out, and then goes inside this transistor and then comes out. So I in the circuit is the same. W over L1 and W over L2 are different. Kn prime, here you have Kn prime, and here you have Kp prime. So W over L1, you will find it as 8. Of course, it's a ratio. Okay. So W is 8 times L. And if you do the same thing, I'm going to just delete, you know, this guy here is going to be Kp, and this is going to be 2, and this is going to be 2. So the same equation, you use it, but substitute Kp prime instead of Kn, and I2 is the same, and W over L2. So you'll find W over L2 to be 32. Is it clear or?
Yeah.
Okay, so that's it.
Just a quick reminder, so the test is gonna be over, or the quiz is gonna be over?
Yeah, the quiz is gonna be over these 2 slides. Okay, the first one, which is the building blocks. Okay, and the second one is the differential amplifier. Unfortunately, we don't have now time to do a differential amplifier, but I can send you another question, like beside the examples we solved in the slides, the one that are the ones that you have in the homework, and I will send you another one. Maybe I was planning to do it today, but time now is over.
Oh, okay.
Okay.
It cut off. What is it that it's going to cover again? Differential amplifiers.
It's gonna cover this part, this slide, differential and multi-stage amplifier, and this part here. Okay, and please, you know, I will send you all the instructions in details, but you need to have a webcam, a cam or a camera in your laptop or whatever that's focused on your workstation and your face. You need to have a scanner or like you can use your mobile phone, like cell phone, to scan the papers and upload them on Canvas. I will show you a link to upload the work, you know, because most likely the exam will be either questions, either multiple choice or just final answer. You write the final answer. So you might sometimes not write the final answer incorrectly, like losing a decimal point or something. So in this, like, I don't want you to lose all the marks. So just you scan your work, you have to write the steps. How did you get the final answer? And then you scan it, and then you compile all the papers in one file, PDF file or Word file, and then upload them to Canvas, so that you don't lose the marks if you just did something wrong when you put the final answer. Okay, so make sure that you can scan and compile compile all the files in one file, all the images in one file, whether using like a scanner or your cell phone, but try to make sure that the quality of the image is good. And also the web camera, okay? Do you like to have an open book exam?
Possible.
Okay, so I'll make it open book. But
Yes.
Open book here means textbook notes, but not surfing the web. Okay, so just you can have your notes, your any textbook you want. Okay, but not, you know, you don't just copy paste and and surf.
So would that affect the test? Like, will it be more tougher for opening?
Yeah, that's what I'm thinking.
Not too much tougher, but you know, it will be like, it's not gonna be directly from the questions in the textbook for sure, you know.
So if it was an open book, it would be.
It will be very similar, you know, like something similar to what you have. Slightly change them. I will change them slightly, not too much.
What if we have a digital textbook?
I will trust you. No, like I trust you to just open this digital textbook, not other things.
Okay.
Okay.
But final point is, if we do the homework completely and we like understand it, we should be fine, right?
Yes, homework and examples in the slides, plus these examples that I've just solved.
Okay, because on the midterm, I did not understand the homework very well. So that's probably, but this homework, at least I understand a lot better.
Okay, that's
so
good.
That's kind of what I was getting at, that if we have enough practice with the homework, should we be fine?
Yes.
All right, okay, thank you.
But again, understanding, it's not gonna be exactly the same, but understanding these equations, you see, we are just using few equations and playing with them. So
yeah,
try to understand how to manipulate these equations to find the final answer.
I absolutely understand what you're saying, but I feel also like the topic we went over today in class, the equations are very limited, and they're used. You just have to look at the circuit and, you know, look at what the VD and VG are. Otherwise, like, it's usually fine.
Okay, so try to like make a cheat sheet or like a sheet of formulas for yourself that you can use in the quiz. Okay, to simplify your searching time. Okay, see you soon in the lab. So for the lab, what we're supposed to do, like today you are gonna do the next lab, right?
I think so.
Yes. You have it on the canvas.
Yeah.
And how about the submission of the previous reports?
I mean, we have to work on that because it's due tonight.
Tonight, right?
Mm-hmm.
Okay. So today we're gonna start. You know, I think this lab is the active filter is gonna take two weeks. Okay. So we'll start today and we'll see like the deadline for submissions. Okay.
Okay.
So most likely next week will be the pre-lab, and you know, like a few days later we can just ask you for the final report.
Okay.
Okay. Any questions?
For the lab that's due today, so for the pre-lab submission, do you want just the calculations, or how do you want it?
Yeah, the calculations and the questions, answering the questions in the let me go to the lab.
You talking about the multiple choice ones at the end?
Yes.
Okay.
Wait, so you want those in the pre-lab? So you don't want them in the full lab?
I remember what did I say last time?
Oh, I don't remember. That's all.
Okay, let me go back here and see the lab. Differential. Okay, differential. Yeah, all the questions that need calculation, okay? Yeah, and the tables, you put them in the table. Not necessary to put them in the table, but in the final lab you have to show these tables, okay? In the final lab report. Okay, just the calculations for now, okay?
Okay.
Leave the questions and everything to the final lab report. Okay? Okay, so see you at the lab time.
All right.
Goodbye.